right, this is circle geometry lesson 3. This is angle properties of a circle. This is our last lesson for this unit. All right, we're switching gears. The first 2 lessons, the properties were about chord lengths, and we used a lot of the Pythagorean theorem. This is going to focus on angles. Okay, so again, I'm just going to remind you that in a triangle, we know that angle 1 plus angle 2 plus angle 3 equals 180 degrees. Okay, so just a reminder of that. All right, let's start talking about circles. Some terminology here. A section of the circumference of a circle is called the arc. Okay, the shorter arc AB is the minor arc. So here we go. Here's point A, and here's point B on the circle. In between them, the pieces of the circle, the circumference of the circle, we would call that a minor arc, AB. But because the circle is round, we could go the other direction from point AB, the long way around like so, and you can see that we would have a major arc, AB. The notation for arc is an arc over top of the letters like this, arc AB. You can notice that that doesn't indicate whether that's the major arc or the minor arc, so that has to be listed somehow, major arc AB or minor arc AB, okay? One other thing about arcs, sometimes there'll be a third letter on here, so like, let's say there's a letter C up here, and again, if I wanted to indicate the major arc, I might give you some road directions that look like this, A, C, B, okay, with the arc symbol. That's telling you you're starting at point A, going through C to B, and that would indicate that that was the major arc. Okay. All right, we need arcs because we're going to talk about central angles. So the definition of a central angle is right here. Let's read that. The angle formed by joining the endpoints of an arc to the center of the circle is a central angle. And in our diagram here, we see angle AOB is a central angle. Again, when you're reading your angle instructions, angle AOB, this is directions. Put your pen on A, go to O, and then go to B. The middle is always the vertex of your angle. Okay? So there's our central angle, AOB, and the word central is right in the description, central angle. We can see that it has its vertex right at the center. So vertex at the center of the circle. Okay, so there's angle AOB, okay, central angle. The angle formed by joining the endpoints of an arc to points on the circle is an inscribed angle. So different kind of angle is called an inscribed angle. If you thought about the word inscribed, if you inscribed into something, you're putting it inside. So this is an angle inside of a circle. So angle ACB is an inscribed angle. So again, here's our directions. C is going to be our vertex. So we have angle ACB. Put my pen on A, go to C, go to B. This is an inscribed angle. So its vertex is on the outside edge of the circle. The inscribed and central angles in this circle are subtended by the minor arc AB. Okay, so that's what I just read over here. The inscribed and central angles in this circle are subtended by the minor arc AB. That word subtended is fancy. It basically means that in between the endpoints of our circle, A and B, here's the arc, and we would write arc AB. Okay, so both that central angle and that inscribed angle are subtended by the same arc. What I want to point out is that their start and end points are exactly the same. That's what we mean by subtended, by the same arc. This angle goes AOB, this angle goes ACB, different vertex, same start, same end. Okay? Now, that information is important because if they are subtended by the same arc, they have a relationship to each other. And here we go. So, first property, central angle and inscribed angle property. In a circle, the measure of a central angle subtended by an arc is twice the measure of the inscribed angle subtended by the same arc. I think that that's pretty fancy language, so we're going to look at the diagram and make it a little bit plain. First of all, I want you to find the central angle POQ. So I put my pen on P, I go to O, and then I come to Q. That's the central angle POQ. Okay, next I want you to highlight the inscribed angle PRQ. So you're going to put your pen on P, vertex at R, another endpoint at Q. Okay, so there's a central angle in blue, there's an inscribed angle in red. What I want you to notice is that they both have P to start, Q to end. That means they are subtended by arc PQ. Okay, so they're subtended by arc PQ. Now, the relationship will be angle POQ is 2 times the size of angle PRQ. So if angle POQ equaled 100 degrees, what would that make angle PRQ? Okay, so angle POQ is the bigger angle. It's 2 times the size of PRQ. So that would make PRQ have to be 50 degrees. Okay? So that was a what if. Let's try another what if. What if I gave you not central angle, but I said that angle PRQ was 42 degrees? What would that make the central angle POQ? Hopefully you've decided that that central angle would be 2 times 42, so it would be 84 degrees. Okay, so in plain terms, the central angle is twice the measure of an inscribed angle if they share the same arc. I'll give you a second to copy that down. Central angle is twice the measure of an inscribed angle if they share the same arc. We want to add a little addendum here. Inscribed angle is half the central angle. Okay, if we want to look at it from the other side of that, inscribed angle is half the central angle. The key here, you guys, I can't stress enough, is again, they share those common endpoints at P and Q. Okay, so we're going to do one more diagram. I'm just going to add a circle down here. You can add it in. Okay, so I'm going to draw my circle. I'm going to center O. And put point A, point B here. And then put point C top here. Like that. Okay, so now if I were to say to you, identify the inscribed angle, what would you describe? Tell me what the inscribed angle is. That would be angle. Oh, I'm so sorry, excuse me. That would be angle ACB. That's the inscribed angle. Okay, and then if I were to ask what the central angle is, you'll notice we're missing an important piece of information for the central angle. We need a center, O. That is going to obviously be angle AOB. Again, A and B, A and B. Okay? Now, if I describe this angle as angle BOA, BOA, I have to stress that those two things are the same. It's So again, it's because they share arc AB or arc BA, doesn't matter which way you say it, they're still the same. Okay, so don't get caught in this rut of, oh, that's B then A, this is A then B, those must be different. No, that's not true. Okay, if I told you that angle AOB was 114 degrees, what would you tell me that angle ACB is? Let's see if you can figure that out. So we're going to take 114 degrees, and we're going to divide it by 2. So 114 divided by 2, and we would get 57 degrees. Okay? So that's the first of our 2 rules. Now go on to the next rule. I said 2 rules, actually there's 3 rules. Inscribed angles property. So in a circle, all inscribed angles subtended by the same arc are congruent. Again, we're using these words, subtended by the same arc. All inscribed angles subtended by the same arc are congruent. And so let's look at our diagram. We're going to start on point P. Just trace with me. P to T to Q. Okay, there's one angle. That's the angle up here, angle T. Grab a different color. I'm going to start at P this time. S to Q. So P to S to Q. That's that angle right there. Thirdly, start at P again. P to R to Q. There's my angle right there at R. Those 3 angles are all exactly the same. Again, P, R, Q. That was my red angle. P, S, Q. That was my green angle. And P, T, Q. That was my blue angle. These are all equal to each other. Notice again, P and Q have those common endpoints. They're subtended by arc P, Q. So when you're trying to decide whether or not these angles are congruent, the best thing to do is to write them out like that. And once you've written them out, you'll see that they have those subtended same arcs, P and Q. Sometimes on the diagrams, if you're trying to just look at your diagram to figure it out, it gets a little tricky. Now, I often call this the bow tie rule because, oh geez, that's a bad circle. What you'll see in a lot of circles is that it actually kind of makes a bow tie shape. So I'm going to put a C and I'm going to put a D up here. So here's angle ACB. So it's angle ACB. And in black, I'm going to draw angle ADB. Angle ADB. So again, look and notice A and B are the common endpoints, A and B. Those 2 angles are going to be equal to each other. C is equal to D. And hopefully you see the little bow tie reference I've made that kind of looks like a bow tie in the middle of the circle. Now, if you could, I want you to think about this upside down for a second. What if I started my pen on D and I drew angle DAC? DAC. Now my vertex here is at A. Put a 2 dash on that. And what if I wrote angle DBC? D to B to C. Okay, little double dash there. Now angle A here and angle B here are congruent. It's the upside down bow tie. They are both subtended by arc DC. Okay, so we can see how that bow tie flips around. All right, how does this work? Well, if I told you this angle up here was 25 degrees, you would then be able to say that this angle here is 25 degrees, and that this angle right here is also 25 degrees. Okay. All right, third circle property, angles in a semicircle. So 2 arcs formed by the endpoints of the diameter our semicircles. So we already talked about that. Here's my endpoints. I know this is a diameter because it goes through center. And I know you guys have heard me say this 100 times this unit, but the angle measure of a straight line is 180 degrees. Now, I know this is going to be difficult to see. I'm going to put an A here, this is an O, and this is a B. If we were to measure that angle, it would be called AOB. It would be 180 degrees. Okay, so from here to there to there. It's just an odd looking angle. Okay? Now I want to draw your attention to my little letter C down here. And if we were to draw angle AC to B, ACB, this is an inscribed angle. This one up here was a central angle. Inscribed angle ACB, well, we know that an inscribed angle is half a central angle. And if my central angle is 180 degrees, then I've just proven that my inscribed angle is 90 degrees. Now, this specific inscribed angle has its endpoints on the diameter. Okay, so we have endpoints on the diameter, and any time we have an inscribed angle that has endpoints on the diameter, we will always know it measures 90 degrees. So here's the inscribed angles in a semicircle property. Okay, it's just what I said. So let's look at angle A to H to B. Noticing that AB is the diameter, and we have our endpoints in angle AHB, A and B, on the diameter. We know that angle AHB has to be 90. Okay, AGB, AGB has to be 90. AFB has to be 90 degrees. Now, what does this mean for us? I would predict moving forward that you need to know this rule to find out if something's a right angle triangle or not, and whether or not you're going to be able to use Pythagorean theorem. Okay? All right, let's do a few practice questions together. So, example 1, we have point O as the center of the circle. We're going to determine the values of x. We're going to determine the value of y. So let's start with angle x. And before we can do anything, we have to look at what we're given. So I want you to notice we're given an angle down here. And I want you to get in the habit of writing the name of that angle. So that is angle ACB. And we know that angle ACB is 55 degrees. Okay? We are looking for angle AD to B. Angle ADB. Okay? Common arc AB. Maybe I should have highlighted this one in blue first. Okay, we got that common arc at AB. So these are inscribed angles. They're not central angles. We'll see that they're not touching the center. So they're touching the outer edge of the circle. We know that angle ADB has to be 55 degrees because these two angles are equal to each other. Okay? All right, let's move on to our y here. So y here in the middle is at AO to B. AOB. Same endpoint, same arc. But the biggest difference is that O is the center of the circle. And because O is the center of the circle, we know that the central angle has to be 2 times the inscribed angle. So the measure of that central angle is going to be 110 degrees. Okay. Right, example 2. All right, rectangle ABCD has its vertices on a circle with a radius of 8.5. The width of the rectangle is 10 centimeters. What is its length? Give the answer to the nearest tenth. Okay, so if we're talking about what we know already, we know that A to B here is 10. We know that O to C is 8.5. Okay? And what we're after here is this length, BC. Okay, a couple of things we can assume in this question. First of all, it's been defined as a rectangle ABCD. Tell me something you know about the angles in a rectangle. Did you all just shout all angles in a rectangle are 90 degrees? I hope so. So I know that this is a 90-degree angle here, and I know the other four are too, but I'm not going to add those to the page. Okay, still not quite there, and I want you to be alert. 90 degrees really is hinting at a right triangle. Okay, can I make a right triangle? Sure I can. What if I finish this to here? What did I call O to A? O to A is also a radius. I already know what the radius is, it's 8.5. So I have another 8.5 centimeters from O to A. Okay? Pulling out my triangle. I have a right angle triangle. I know this is 10 centimeters. I know this is 8.5 and 8.5. That would be 17 centimeters. Now I just need to find that missing side length. How am I going to do it? Hopefully you're all shouting Pythagorean theorem, the only theorem we know here. Now, I already know the longest side. How do I know this is the longest side? Because it goes right through opposite the 90-degree angle. That makes this the longest side. Because that's the longest side, I'm using subtraction. 17 squared minus 10 squared equals x squared. Go ahead, grab your calculators. Figure that one out for me. So we're going to do 17 squared, take away 10 squared. So 17 squared, take 10 squared. I get 189. So 189 equals x squared. So I root that. And it says to the nearest tenth, I get 13.7477. I go to the nearest tenth, I look at this digit, 13.7. Don't forget your units. Oops, centimeters. Okay. I accidentally slipped my page down there, but I just want to show you a polygon whose vertices lie on a circle is an inscribed polygon. In example 2, rectangle ABCD is an inscribed rectangle. That means rectangle ABCD is inscribed in the circle. Just an extra note. What that means is this rectangle has all of its endpoints on the edge of the circle. That's what an inscribed polygon is. So it could be a triangle inscribed, or a rectangle, or a hexagon, whatever we have, as long as all vertices touch the edge of the circle. Okay, another example. Triangle ABC is inscribed in a circle, center O. We know that AOB is 100, COB is 140. We're going to determine the values of angle X, Y, and Z. Okay, we're going to start with angle X, and I'm going to do the work and I'm going to erase so that you can see the triangle again. The reason I'm picking angle X is because I have this as 100, and I have this given at 140. Now, we know that a complete circle is 360 degrees, and so if I were to draw one complete circle here in the middle, I'm just missing this little piece here for X. So all I would need to do to find that other angle is take 360 and subtract 140 and subtract 100. Grab your calculator, do that. And we get angle X. Okay, it's 120 degrees. That one's pretty straightforward. Just going to erase my circle work here so you can see the circle again. Alright, let's go after angle Y. So I want you to notice that it looks like angle Y has the mark right across there. So it's actually both of those little angles. Okay, so I want you to see that it's both of those little angles. I think that means we're going to have to go after, oh, no, we can do this. Okay, because it's both of those little angles, I'm going to divide this into two parts. I'm going to find this little angle here and call it angle 1, and I'm going to put a little 2 up in here. We're going to find angle 1 and we're going to find angle 2. Luckily, it's going to be exactly the same process. If I start with angle 1, it looks very difficult, but I'm going to focus on this triangle right here, B to the center O to C and across. So I'm just focusing on that kind of skinny little triangle. Notice the 140 here in the middle, okay? Now, we had this discussion in class a couple of days ago. O to B is a radius. O to C is a radius. Because they're both radii, they are congruent to each other. So that's an isosceles. I can't spell isosceles. Isosceles triangle. Okay, that's an isosceles triangle. Because I know that this angle is 140, I know that this angle here and this angle here are equal. So if I take 180, subtract 140, I have 40 degrees left that has to be shared between those two angles. Okay, so if I have 140 left to share between those two angles, I have to take 40 and divide it by 2, and I get that one angle that we're calling angle 1 to be 20 degrees. Okay? Now, again, in change colors, we're going to focus on this triangle now. A to O to B. That's going to help us find this little angle 2 that I'm calling it up here. Same thing. This is O to B. This is O to A. They're both radii. They're both congruent, which means I have another isosceles triangle. And now I've used up 100 degrees of my triangle. So 180 subtract 100 means I have 80 degrees left to use. I have 80 degrees that has to be shared between those two angles. So I take my 80 degrees and divide it by 2, and I get 40 degrees, and that's what angle 2 would be equal to. But remember, we're actually trying to find a combination of the two of those. So we would add them together, and we would get 60 degrees. Okay? So angle Y is 60 degrees. Almost done. Angle Z. Angle Z is nice and easy. Now we know how to do this. Angle X, we figured out, was 120 degrees. Again, look at O to C. Look at O to A. Radii. Radii. We have another isosceles triangle. This time I've used up 120 degrees of my 180. So I have 60 degrees left to play with. 60 degrees between those two angles. 60 divided by 2. 30 degrees. That's what angle Z is going to be. 30 degrees. All right, we have 2 classes to work through angle properties together. This was a pretty long lesson with lots of examples. We'll pick this up in class tomorrow. Just bring your books, make sure you have your notes done, and we'll try some practice in class. Have a good day.